Good morning. Today we will be discussing Gaussian processes, which are one of the most powerful Bayesian non-parametric methods. Now we technically haven't studied what's a non-parametric method. Without going into much detail, I'll give you a very quick introduction to parametric methods. So these methods can adapt to the data. So this is to say that if you have more data, these models can learn more complex decision functions. Unlike linear regression, where no matter how much amount of data you give, the model that will be learned would still always be a line. Of course, the parameters can be changing, but it will still remain a line. But in non-parametric methods, based on more data, you can learn arbitrarily complex decisions. And Gaussian processes are also Bayesian in nature. We'll see in a while why they're Bayesian in nature. Before delving into Gaussian processes, we'll do a very quick revision of Gaussians, multivariate Gaussians, some of the properties, and then we'll be able to form the necessary background to understand Gaussian processes. So we'll go to the 1D Gaussian distribution, and this plot is showing, this is a scatter plot showing some samples from a 1D Gaussian. While it might not be very accurate, but there are more samples towards the mean, which is close to 0, as compared to the number of samples further away from the mean. And the same thing can be visualized using histogram also, which is showing us the normalized frequency. There is much more probability of drawing samples close to the mean. So this is, I believe, a normal with a mean 0 and variance 1, and thus you'll see very few points outside. So the points, as you move further away from the mean, the number of samples would be much lower. Now, histograms suffer from the difficulty in interpretation, and that they're dependent on the width of the bar. So if you were to choose a different bar width, you might see a different looking histogram. So what's often done is to use something known as kernel density estimation. These points, these three subplots are showing the kernel density estimation, which is, so just think of it as a smoothed out version of the histogram. And so what you're seeing here is the probability distribution with means of a 1D Gaussian with mean 0 and variance 0.5. So it's pretty much concentrated towards the center, and it's much more pointed compared to the other distributions, and you see a lot more point samples very close to the mean. If you increase the variance, you'll see that the probability mass gets divided further into the space away from the mean, and if we increase the variance furthermore, you will see that the probability mass is even more spread out. Let's now look at bivariate Gaussian. And bivariate Gaussian, we very briefly discussed bivariate Gaussians in another previous lecture when we were discussing about so in two of the previous lectures. One where we have discussed about the normal distribution. Second, where we were discussing about entropy, specifically differential entropy. So I'm defining a bivariate Gaussian here as normal with a mean vector mu, which contains mu1 and mu2, and a covariance matrix, which is given by A sigma sigma B, where A and B are denoting the variance of x1 and x2. So I think I have these written in the reverse order. And rho is denoting the correlation between x1 and x2. So rho varies between -1 and 1. Now we could also draw another beautiful visualization to try and understand a bivariate Gaussian. Here the covariance or the correlation between, so here this rho value is positive, and so what you're seeing here is, so this plot, you're seeing that it's a scatter plot showing the samples drawn from this bivariate Gaussian, and the plot on the top is showing the marginal distribution of x1 So this is the distribution of x1 considering all possible values of x2. Because Gaussians are closed under marginalization and conditioning, thus the marginal of x1 is the marginal x1 is also a 1D Gaussian. Now this marginal of x1 is a 1D Gaussian with a mean mu1 and a variance of a. Similarly, x2, which is the marginal, is a normal with a mean mu2 and a variance b. So you can very clearly notice that both of these, x1 and x2, the marginals are also 1D Gaussians. And here we see that the rho is fairly positive in quantity, and thus there seems to be a positive correlation between these two random variables. In this example, we see that the correlation between these two random variables is negative, and we can still see that both x1 and x2 are 1D Gaussians. In this particular example, the two random variables are uncorrelated, which means that rho is almost tending towards 0. When we discussed about differential entropy and mutual information, we saw that if we know one of the random variables, let's say x1, then the information we get about x2 is 0 in such a case, because both of these are uncorrelated. The other way to look at this, the same kind of plots, is to look at a surface plot and a contour plot combination. The surface plot is now plotting the probability density function in a 3D space where the height tells us the probability density, and x1 and x2 are represented using the two dimensions x and y, and corresponding to this mountain looking PDF, there is also a contour which we can plot. So one thing which we should be very careful here is that the contour is over the probability density, right? And this is a surface and contour plot for a 2D Gaussian with mean 0, 0 and a covariance matrix of 1, minus 0.5 and minus 0.5 and 1. So there is some correlation, although negative in this case, between x1 and x2, which is also apparent from the contour plot if you see. Whereas if you make a contour plot of a bivariate Gaussian without any correlation, so it would look something like the following. Now let's try and visualize some samples from 2D Gaussian to form the basis for Gaussian processes. So I'm going to look at this particular kind of visualization. On the leftmost, I have a covariance matrix for this case, which is so the individual variances are 1 and 1 for x1 and x2, and the correlation is 0.1 in this case. I have made the contour plot, which is the same as the contour plot I've been showing over here. So this contour plot is now in this 2D space, and I've marked one black point. So this black point is one sample drawn from this bivariate Gaussian, and the rightmost subfigure is an interesting way of visualizing this sample. So if you look here, we have x1 is close to minus 1 and x2 is close to minus 1.5, right? So to visualize this, I make this new plot where I mark x1 and x2 as two variables on the x-axis, and on the y-axis I plot the corresponding values. So I mark x1 as close to minus between something close to minus 0.9 and x2 as something close to minus 1.5. So I have marked this point, and here the covariance was 0.1, right? So let's look at another such point. Now this point has x1 close to 0.3 or 4 and x2 close to 0.3 or 4, something like that. So we can again visualize this point. Let's look at another such point. Here x1 is close to minus 1.7 and x2 is close to minus 1. Yet another point, x1 close to minus 0.5 and x2 close to plus 0.4 or so, right? And yet another point. So let me show you this in a notebook that I've written on Gaussian processes. By the way, all the plots, all the figures have been generated using this notebook itself, as you may have been seeing. So let me show you this particular animation, which is showing for this particular covariance matrix. These are the points that are being generated. So I would encourage you to look at only the rightmost point at this rightmost plot at this point. What this is showing is that the correlation between x1 and x2 is weak. So it's only 0.1. Thus, for any value of x1, x2 seems to be wiggling a lot. So there seems to be, they seem to be almost moving independently. Right? That is why this plot is jumping all over the place. Let's try and understand this plot for the case where the correlation is much more positive. Okay, let's look at this case. Here the correlation between these two random variables is 0.7, and you can of course see that the contour in the previous case was almost like a circle. In this case it's much more elliptical and much more along the line y equal to x, something like that, which can also be visualized from this final subplot, which is showing that x1 and x2 values are fairly similar. So if x1 will be, let's say, minus 1, x2 will be very close to minus 1. So this is a very interesting visualization which will help us to build up the basics for Gaussian processing. Okay, having studied sampling from a bivariate Gaussian, let's now try to understand conditioning on a bivariate Gaussian. So again, remembering what is the difference between marginalization and conditioning. Marginalization means you're marginalizing out or taking across all of the possible values of the other random variable to see the distribution of one random variable. And conditioning means you fix the value of one random variable. So what I'm saying is that given this bivariate Gaussian with a mean 0, it's a vector 0, and the individual variances of 1 and the correlation of rho, the conditional expectation of x2 given x1, or the expectation of x2 given x1 equal to small x1 is rho small x1, and the conditional variance is the variance given x2 given at x1, capital X1 is small x1, is 1 minus rho squared. Now this is following directly from the derivation for marginalization and conditioning for 1D Gaussians, which you can study from the Wikipedia page. What would be interesting to note would be, let's try and visualize this phenomena. So I'll go back to the notebook again. Okay, so what I've done in this is I have fixed x1 to be 1, right? So fixing x1 equal to 1 is shown in red, and I am still drawing samples from this joint distribution, but I've conditioned on x1 to be equal to 1, right? So what this is effectively doing is now just drawing the points for x2 and such that x1 is 1, and if you visualize from the rightmost plot, you'd see that x2 is varying quite a lot, right? So any thoughts on what would be the mean of x2? So now I've mentioned that x2 condition on x1 equal to 1 would also be a 1D Gaussian. So it will have a mean and it will have a variance. It seems that the variance is very high because we can see that x2 is jumping all over this point. But if you notice, x2 is mostly having a lot of points over here, right? So we said that the conditional expectation of x2 given x1 is rho x1. Rho was 0.1, x1 was 1. Therefore, the mean of this conditional distribution of x2 given x1 equal to 1 is 0.1, and the variance is 1 minus rho squared. Since rho is really small, 0.1, thus the variance is almost 1 in this case, which also seems to be fairly visible that there is a lot of variance, but the mean seems to be close to 0.1, right? Let's try and do the same visualization with a covariance matrix where there is much more positive correlation between the random variables x1 and x2. So this is that particular case. Here we can see that having fixed x1 equal to 1, x2 is not varying a lot. It is fairly close to, first, it's fairly close to x1 equal to 1. So in fact, the conditional mean is 0.7 and the conditional variance is 1 minus 0.7 squared, so almost 0.5. So that is also very apparent that the amount of jumping around of x2 given x1 equal to 1 is much lesser in this particular case compared to the previous case where the covariance matrix was such that the correlation between x1 and x2 was much lesser. Okay, having studied this, we'll now, having studied a bivariate and having drawn some intuition into the conditioning, we'll be now looking at a 5D multivariate. So the 5D multivariate would be pretty much on the same lines. I'll first show you a plot of that. So this particular slide is showing a covariance matrix. And like before, I have drawn a sample from this 5D Gaussian. Of course, I cannot now draw this contour and show it in, project it in 2D and show you. But this is effectively showing you that you have 5 different dimensions, and this is the sample draw. So you have one sample, which is x1 equal to minus 1.5, x2 equal to minus 1.6 or so, and so on and so forth. Right? What we can observe from this covariance matrix is that the correlation between x1 and so on the covariance matrix I'm showing the indexing from 0 through 4, whereas here I've drawn from 1 through 5. So you just need to do an offset here. The correlation between the first random variable and the second random variable is 0.9, very significant, which means that x1 and x2 will largely be fairly close in terms of their values. But if you go far, so you look at the first random variable and the last random variable, they can be significantly different because the correlation between them is not very high. So let's try and now draw some samples from this 5D normal 5D Gaussian distribution. You can see that, so if you look at all the possible values, all the possible samples from here, you'll see that x1 and x2 will almost always move up and down together. But x1 and x5, since they are not that significantly correlated, they'll seem to be wiggling around almost independently of each other. Now, having studied the bivariate distribution and its conditioning, and having seen the multivariate 5D multivariate Gaussian and a sample from it, we'll now be doing a conditioning on any multivariate distribution on a with dimensions greater than 2, and for the purposes of simplicity, we'll be using this same 5D multivariate Gaussian for some illustrative purposes. So in this conditional multivariate distribution, I'm going to say that we have an n-dimensional x, which is partitioned as follows. So in our case, x is currently, in the previous animation that I showed, x is currently 5 dimension. So I'm partitioning it as x sub a and x sub b, which is of size q cross 1 and n minus q cross 1, right? And I'm defining mu and sigma as mu a and mu b with sizes q minus q cross 1 and n minus q cross 1. So total there are n dimensions, right? And xa has q dimensions, has, yeah, so xa is q dimensional and thus xb is n minus q dimensional. We're going to be writing this covariance matrix. So we have the original covariance matrix was of size n cross n, right? Because you have n points, n dimensionals. So the covariance matrix is n cross n. We are now breaking down this or partitioning this covariance matrix into 4 such blocks, right? The first partition is sigma A. Now since A is a q dimensional random variable, thus sigma A is defined as a q cross q matrix and sigma AB is a q cross n minus q matrix. So think of it as you'll eventually want n rows and n columns in the sigma matrix. So you've already given q columns to sigma A, thus n minus q columns are left for sigma AB, and you've given q rows to sigma A, thus you're left with n minus q rows for sigma BA, and finally you have a sigma BB term, which is a n minus q cross n minus q matrix, right? And now we'll be applying the properties of conditioning. So what we're saying is we are setting x sub b equal to small b. So this is not a single value now, it's a vector that you are setting. So basically you're conditioning on a subset of the multivariate Gaussian that you have, right? And what we're saying is that the distribution of x sub a conditional on x b equal to b is again a multivariate normal with a mean of mu bar and a covariance of sigma bar, where mu bar is given by mu a, which we have already seen before, plus the sigma AB term. By the way, if you've not seen, not understood thus far, sigma AB and sigma BA, do you see any relation between them? They'll be effectively the same thing, just transpose of each other. So mu bar is mu A plus sigma AB times sigma BB inverse multiplied by B minus mu B. Now this is a fairly involved derivation. I'll hopefully be able to share the link for the derivations for this. And the covariance matrix, or the covariance after this conditioning, is sigma A minus sigma AB sigma BB inverse into sigma BA, right? So the mean of xa conditional on xb equal to b is dependent on mu a and mu b, right? Sigma hat, if you see, does not depend on anything. So it does not depend really on mu a. So what we'll be doing is now fixing x5 equal to minus 2, right? So if you fix x5 equal to minus 2, could you think about the sizes of mu a, mu b, and sigma a, sigma ab, sigma bb? Right. So sigma a is, xa is now x1, x2, x3, x4. It's a 4-dimensional normal random variable, 4-dimensional random variable, and xb is x5. Thus, we can refer to as this sigma a as, so the entire 5 by 5 covariance matrix is referred to as C, Sigma A will be now the covariances between the between the first four covariance matrix defined on the first four random variables, the C11, C21, C31, C44 till C41 till C44. Sigma ABB will be having the cross terms. So this will be talking about these four random variables C1 through C4 and the covariance with the variable which we have conditioned on. So that is x5. So this will have C1, C2, C3, C4 and C4, 5. And sigma BA is just the transpose of sigma AB. Sigma BB will contain only a single term in this case, which is C55. So thus in this we have Q as 4 and N as 5, thus N minus Q is 1. Now what we're saying is I'll be just plugging in these numbers given this covariance matrix that we have chosen and conditioning on x5 equal to 2. Let's try and see what we'll get. So I've just plugged in this numbers. So firstly, if you notice, I've defined sigma AA to be covariance of the original covariance. We're just taking the first four rows and the first four columns. Sigma ABB, I'm taking the first four rows and the last column. And sigma BA is just the transpose of sigma AB. And sigma BB is just the last row and the last column in this case of the original covariance matrix. We can calculate mu bar as mu A. So mu bar is mu A plus sigma AB times sigma BB inverse P minus mu A. I've just kept mu A to be 0 and mu B to be 0. And thus I'll get mu bar to be zeros of 4, 1 plus sigma AB into sigma BB inverse and times B minus mu B. So this B is the conditioning that we have. So this conditioning is a 1 cross 1 value in our case, which is just minus 2. So one small change, this xb equal to small b should actually be xb equal to capital B, or you just replace this capital B with small b just to make things consistent. So sigma bar we'll get a mu bar value this way, and if you notice the mu bar that we're getting is minus 0.8, minus 1.2, minus 1.6, minus 1.8. So this is the mean of the four random variables x1 through x4, and if you notice carefully, then the mean of the fourth random variable is minus 1.8, which is fairly close to minus 2, right, which was the conditioning that we had. If you go back and look at the original covariance matrix, the correlation between the last two random variables, that is x4 and x5, is 0.9. So does this make sense? If you have if you have a value of minus 2, then the value of the closest random variable with a significant correlation, in this case which is x4, should be fairly similar to the conditional value. We can similarly calculate sigma bar just by plugging in the formulas, and it will come out to be a matrix which looks like the following, right? So we'll now be visualizing by conditioning on x5 equal to minus 2, and we'll be now looking at some samples drawn from this new conditional distribution. So the conditional distribution is now a 4-dimensional normal distribution with a mean of this minus 0.8, minus 1.2, minus 1.6 and minus 1.8, and a covariance matrix which is given as follows. Okay, so this is the visualization of this conditioning. I've fixed x5 to be minus 2, and you'll see that x4 will be fairly close to x5 always. So the mean of x4 looks to be between minus 1 and 2, although tending more towards minus 2. But if you'll notice that x1, since x1 is not that well correlated with x5, it will wiggle a lot, and the variance for x1 would be the highest also, right? Which can also be observed from the covariance matrix. So the covariance matrix also shows that the variance for the first random variable is the highest, which again makes sense because you've only been able to now fix or condition on x5, and as you move further away, you have very little information about this. So the covariance would be high in such cases. Now, what I'll do is to increase to 20 dimensions now. We've just done a visualization over 5 dimensions. Now let's do the same process for 20 dimensions. Now, I didn't want to write the covariance matrix for 20 dimensions. It's a fairly involved process, but there's a trick that is typically being used to generate such covariance matrices, and this is using a kernel function. Kernel function will get used a lot when we study SVMs also. For now, just think of it as a way to create the covariance matrix, which should be a positive semi-definite matrix. So I've just used something known as an RBF kernel, which given two inputs, x1 and x2, and sigma, it just returns the exponential of x1 minus x2 the whole squared, negative exponential of x1 minus x2 whole squared, the entire thing divided by 2 sigma squared. Right. So what I've done is, what we're trying to do is, for if x1 and x2 are differing a lot, then this function should return a low number. So what this is effectively saying is that if we are looking at two random variables, if they are closer, so which means x1 and x2 are close, then the covariance return should be high, but if they're far away, then the covariance return should be low, and the tuning parameter that we're using here is sigma. Right? So what I've done, I've shown an illustration, is I've applied the RBF kernel as per this definition, with x1 equal to 1 and x2 equal to 2, so both of them are the same, and we're returning number 1.0. But instead, if we used the same function evaluated over 1 and 2, which are now separated to some extent, the function will return 0.92, and I could vary this sigma parameter. If I increase the sigma parameter from 0.4 to 1, now the number returned is 0.6. So which is effectively saying that now we have dropped the correlation between x1 and x2 being 1 and 2 by increasing sigma, right? So what we'll see is the maximum value that we want to get is 1 in such cases. So now I'll create a covariance matrix of 20 by 20 using this kernel function. So I've just initialized an empty covariance matrix of size 20 by 20, and I've set the ith row and jth column to be the evaluation of RBF kernel of ij, and sigma to be 0.5. And if you plot the heat map and you look at the corresponding values, you'll see that along the diagonals you have all ones, which makes sense because the covariance between xii should be 1 in as per our definition. And we see that there is some amount of correlation between adjacent cells, like between x1 and x0 there is some correlation, between x1 and x2 there is some correlation, and there is then falling correlation between x1 and x3, even further reduced correlation between x1 and x4, and so on and so forth. So you generally see entries along the diagonal, and then there are some, in some vicinity you'll see some points. So we'll now be visualizing some samples drawn from this 20-dimensional Gaussian, which is effectively the same thing we've been doing thus far. Okay, so this is now showing some samples drawn from this 1D Gaussian. So it seems like a fairly wiggly snake, right? So what we are effectively seeing is that we are now seeing a family of functions. So I initially set the mean of this 20-dimensional Gaussian to be 0, and I've specified some covariance matrix as per the kernel function, right? So what I'm effectively saying is that I'm now seeing, so think of it as a very smooth curve that we've drawn. So I'm seeing a family of such curves where each member is a sample from this uh, 20 variate 20-dimensional multivariate Gaussian, and each of them is now representing some relation, right, or some it's showing some samples drawn from this, and this is basically a family of functions that we have now obtained. So we can now, as usual, condition on a few elements as we done in the 5-dimensional case, and this conditioning would I'll directly take you to the result. Now what I'm showing you is the conditioning on x1 equal to 1, x2 equal to 3, x6 equal to -3, x11 equal to -1, right? So what you might see is that the condition points are firstly shown in red. The points close to the condition points will vigor very less, and their means would be fairly close to the means of to the conditioned to the condition value of the closest point. But if we move to points which are very far away from any condition point, we'll see that there is a lot of fluctuation in terms of the samples drawn, right? So what this plot is showing is the uncertainty or standard deviation and the mean values for the different variables. So this is effectively the same plot, but I've just applied the Gaussian conditioning formula, and I'm showing you the variances amongst the different points. So as mentioned earlier, the variances for points which are fairly close to the condition points would be low. As you move away from condition points, the variance will keep on increasing. Right. Okay, having studied about creating a covariance matrix, we'll be now doing a very quick overview of what kernels are. We'll not go into much detail in this lecture. Maybe in a future lecture, or when we discuss about support vector machines, we'll go into much more details. So the only thing we limit our discussion is to if kernel function is a function which is used to generate the covariance matrix. So I'm now defining another function which is uh, used to generate a covariance matrix. As expected, it should have as inputs 2 points x1 and x2 between which you're trying to draw the correlation. And in this particular formula that I have two parameters. One is s, which is a scale of variance, so which is telling you how much variance you'd have at any point. So for example, this has more variance. If I increased an s parameter, each of them will have more variances. And the L parameter is the influence of a point to the neighboring points. So what this is effectively telling is that how much smoothness there is. So if you add a lot of smoothness, then knowing or conditioning on, let's say, x2 equal to 3 would tell me a lot about even very far away points, let's say x8 in this particular case. So what I've now shown is some different covariance matrices being visualized over varying L parameters. So I fixed S equal to 0.1 and I varied the L parameter. So if I keep L as very small, what that means is that there is a lot of influence of any given point to very far away points also. So that's shown in this covariance matrix. If I keep L to be very high, then I'll get entries mostly wrong on the diagonal, and all of the remaining entries to be 0, which means that a point has very local influence. It does not, the influence does not go very far. In the next plot, what I'll do is to fix L equal to 0.1, and I can vary S scale. So what you now see is uh, see the range of values that you can take. For S equal to 1, you're going from 0 to 1. So this is the magnitudes in the covariance matrix. Keep S equal to 10 and you're going from 0 to 100. Keep S equal to 20, you're going from 0 to 400. And keep S equal to 30, you're going from 0 to 900. So you might have already noticed that we go from 0 to S square. That is the range of values that we have. So what I'm now showing is that I am conditioning on the same set of points which I've done previously, and I'm now plotting the prediction, or I'm just plotting the high dimensional Gaussian, the 20-dimensional Gaussian, using different set of parameters to create the covariance matrix. So in this case, I'm using L equal to 0.5 and S equal to 1. And you can see in the shaded region, I'm showing the uncertainty, or in this case, I'm just showing the variance, right? If I change from S equal to 1 to S equal to 5, now if you notice carefully, you'll see that now the variance at every point has increased, right? So another thing which you might have already discovered or noted is that the variance at condition point is 0. That makes sense because you've observed that point. There is no amount of variance in this case. In few minutes, we'll see a case in which we can have some variance even about the conditioned points. But for now, we'll just leave it as it is. And now what I've done is I've changed going from L equal to 0.5 and S equal to 1 to L equal to 1 and S equal to 1. So what we've seen is that increasing L will reduce the influence between faraway points. So that's something which we had just seen a few minutes back. If you increase L, then the covariance matrix becomes much more aligned only along the diagonals, which means that there is much lesser correlation between faraway points. And now I've increased L to be even more. L is now a very large value, right? So with this very large value, we're seeing that there is, we see that the data, the values are just hovering around the mean, right? The mean that we had given, which was zeros. So could you think about why this is the case? You should be thinking about the case of the Gaussian update or the Gaussian conditioning formula. So from that, you'll get some intuition as to why we're seeing what we're seeing. So with this background, what I'll do is to show you another animation. So in this animation, what is happening is that over time, I keep on adding different points, right? And we see that the uncertainty in the whole region keeps on reducing as expected, because once you've conditioned, you reduce the uncertainty to points in the vicinity of the condition point, right? Now, what this plot is also showing is the basis of Gaussian processes, which we'll just hold on for a second and we'll come back to this again after having looked at some theory. Okay, so I'll finally now formalize what Gaussian processes actually are. So a Gaussian process is a model, is a Bayesian non-parametric model, which is fully specified by a mean function and a covariance function, where each x is a vector and f is a real valued function. So x could be n-dimensional, and function of x, the evaluation is going to be a real number. So thus far, the first thing which we'll see in Gaussian processes is the simple assumption, which is known as the noises GPs. So don't worry if you've not understood this, what I've written thus far. Just let it evolve over a few more minutes, and we'll understand both of these things better. So we'll be considering the case of noises GPs, and what we assume is that we receive for every particular x, we receive a single functional value of fx, which means that there is no noise in a function. So which also means that, let's say if we've conditioned on one particular variable, then there is no variance about that value. So we definitely know the value of observation at that point. There is no noise in the system in terms of the observations. So coming to the formalization of GPs and trying to understand this better, that where is the training going on and where is the prediction going on. So we'll start off with some training data, let's say, which is tuples xi comma yi from I equal to 1 through n. And what we want to do is to, for a given test set, x star of size n star cross d, so d dimensional input, and we have n star test points, and we want to predict the function outputs y star, right? We have n points in the train set, which is the train set x, which is of size n cross d, and we have n star cross d points, and so we have the test set x star of size n star cross d, right? So this is where the beauty of Gaussian processes comes in, and this is how it relates to multivariate Gaussians. What we say is that we can write this entire n plus n star set of points as a n plus n star dimensional Gaussian, where we have observations or we have the training data, which now works as the Gaussian as the conditioned set of variables. Right? So we have mu as the so basically just write down this Gaussian multivariate Gaussian formula. So y and y star. Now both of these are vectors. You should know it's not a single point. Y is the output labels or the output predictions, because we're dealing currently with the case of regression for n points of d dimensions, and y star is the prediction that we want to have on the n star points. So we write this entire system as a multivariate Gaussian with a mean of mu star, which both are vectors, and a covariance matrix, which we've seen before is partitioned along four submatrices. The first submatrix is K. So the K is basically the evaluation of the kernel function over the input x and the input x. So it's basically the kernel evaluation of x, comma x. This would be n cross n dimensional submatrix. K star is the kernel evaluation over x and x star, and K star star is the kernel evaluation of x star and x star. So basically K is the kernel evaluation over all the train points. K star is the kernel evaluation of each train point with a test point, and K star star is the kernel evaluation between all the test points, right? So what we say is, now this is exactly same as the Gaussian conditioning that we'd seen previously in the case of bivariate Gaussian, and when we discussed about partitioning. So what we say is that the probability of y star given x star, so x star is the input for the test points, and x comma y are the train inputs and the train outputs respectively. So this is given by a normal with a mean mu tilde and sigma tilde, where the main post conditioning, so the conditioning is based on the observations that we have drawn, which is x comma y. So the main post conditioning is given by mu star plus k star transpose k inverse into x minus mu, and sigma hyphen or sigma tilde is k star star minus k star transpose k inverse k star. Now you should just go back a few slides and verify that this is the exact same thing which we've written previously. But this definition that we've thus far seen is much more aligned towards writing our own function in a scikit-learn like API, right? So I'll now try and first show some code. So what I'm now trying to do is to show you a scikit-learn like function containing a fit and a predict method. So we have defined formally what is a GP, right? And I'll be using this previously defined kernel. And these are the update rules. So this, based on this, we'll be making some prediction, right? So all I need to do is to compute all of these terms. The kernel function k, k star, and k star star is what I need to compute. So what I'm given is this kernel, what I've used is this kernel definition based on L and S. The fit method is given the argument train x and train y. And if you remember, I mentioned that the kernel matrix K is the kernel function evaluation over x and x, right? So K is the kernel function evaluation over x and x, which is the n cross n dimensional matrix. So that's the only thing which we can learn as such from train x. Now, only once you're given the test points do you start computing all of the remaining terms in the expression. So in this sense, Gaussian processes is a very different kind of an algorithm. Now you've not learned something explicitly from the train set thus far, and only once you've given the test set do you start the kernel function evaluations on the test set and the compare and on the train set, and based on that you apply the Gaussian conditioning formula. So first, previously I defined self.n as the length of train x. I can get n star as the length of test x. Now I'll be defining k star to be the kernel function evaluated between the train and the test. So if you see, it's between the train x and the test x with the kernel parameters. K star star is the kernel function evaluated between the test and the test, and posterior mu is the mean. So mu tilde or is mu star plus k star transpose k inverse x minus mu. Now all I've done here is to predict this using k star dot transpose and k inverse multiplied by train y minus the mean over the train set, right? And similarly, I can find out the covariance matrix for the test points also, which is exactly what I have done over here. So just use the same formula which I've mentioned above. Now, what I'm doing here is now to instantiate this class, noiseless GP inversion, and I've defined a train x to be 5 points of one dimension, so which is -4, -3, -2, -1, and 1, and train y is the sinusoid over this train x. So the ground truth function I'm using here is the sinusoid, and I'm evaluating now. I'm trying to predict the corresponding y's at all the x's between -5 and 5 sampled. So there are 50 such samplings, right? So between -5 and 5, I'm trying to see what is the prediction at each of these points, and this is what we end up learning. So we have the ground truth function, which is sine of x. I have some training data. I have very few training data. If you see, I have just 1, 2, 3, 4, 5 points, and I've chosen some sample values. I've chosen some values. So in fact, if you see, let's see, we have a test x. Train x, train y. Yeah, so what I've shown is that I've set the prior mean to be 0. So that's typically very often done in Gaussian processes implementations, GP regression implementations, because even if the data does not have mean 0, you could always center the data and just use the prior mean equal to 0. The tricky thing, which is often the tricky thing often in Gaussian processes, how do you choose the kernel function? So in this lecture, we are not going to discuss that, but I just wanted to show you that it's often good to just use the prior mean to be 0. Of course, I've not yet defined why it is called a prior mean, so if you just hold on for a second, I'll come to that. What you're now seeing is the predictions, and you can of course see a lot of variance also. So you see that since at this, all of these points from x equal to, so from 1 through x equal to 5, there is no other sample point. There seems to be a high amount of variance there, and the prediction is naturally not so good. But anyway, close to the points, so if you look at from x equal to -4 to x equal to -3 or so, you have enough points. The prediction is fairly good, right? So this now brings us to a very interesting point, that what is the Bayesian component of Gaussian processes. So I'll take you back to the slides. So if you remember the Bayesian setting, there is a prior, there is some data, and then there is a posterior. So what do you think is the prior over here? So in fact, for Gaussian processes, we have a prior over all possible functions which could have been fitted to a given data. So I'll be showing this using, so this is a very beautiful article on distill.pub on a visual exploration of Gaussian processes. I'll go down in this article and show you what I meant. So imagine you have a high dimensional Gaussian, right? Let's say 20 dimensional Gaussian that we've been seeing thus far. So you've defined some parameters of this Gaussian, which is the mean and the covariance. So we say that this is the prior set of parameters for this high dimensional Gaussian. It's the prior because you've not observed any data. But from this prior, could you draw samples? Yes, of course you could. And that's what we've been doing for a long time. So if we go back up, we go to the 20 dimensional Gaussian, let's say. This is the condition, right? If you look at this plot, now this is a 20 dimensional Gaussian, and this is just some random samples drawn from this. So what this is telling us is this is the set of possible functions which could be drawn from this high dimensional Gaussian, right? So you could have a lot of these functions being sampled. So this is the prior over all the possible set of functions which could have been fitted, which you could fit to the data. So this is interesting and different from all the previous settings in which we have applied Bayesian. So again, remember, this is a prior over all possible functions which could have been used to fit the data. But once you observe the data, let's look at this case. You've observed some data. So the red points are the data observations, right? So you had a prior, which was all of these possible functions. Now with the data, you will get a posterior. which means that you'll now be having a different set of functions which have also incorporated the data that you have, right? So now if you notice that the set of functions which are being drawn from this high dimensional Gaussian is different, right? Because you have done some conditioning, or you've passed in the data. Based on that, the observations, the samples that you'll draw from the all possible set of functions has changed. So let's look at this animation again to try and understand this. So what you see in purple color is one such function drawn from this high dimensional Gaussian. If I click here, you'll see that you can draw many more such functions. Of course, you'll see that they seem to be always in a particular range, and they seem to have mean 0, so which is exactly by the setting, right? So you can keep on drawing some functions like this. And what you can also do is to now, so what I'm showing in this is exactly the same thing. You're now trying to draw some different functions from the prior, right? You have not observed any data, but let's see if you observe some data, right? If you observe some data, now you see that all the possible set of functions which could have been defined on this space have to pass through this point. That's primarily because we have assumed a noiseless case. So, and you've conditioned on this point. So now all the possible set of functions that you could have drawn has changed, and the covariance matrix has also changed. You can see a correspondence between these two. What I'll do is to now sample another, I'll condition another point. Now if you see, the set of samples that you can draw has again changed. So it's much smoother in the region between these 2 points, which makes sense. So thus we have a prior function, which means we have a prior mean and prior covariance, and the data is our observations, and the posterior is the possible set of functions which comply with the data, given that you've started with a prior. Right? So this is the Bayesian setting in which Gaussian processes are applied. Now, if you had seen my implementation, so I was doing a lot of matrix inversions. So which is one of the pain points of Gaussian processes, and it's one of the reasons why Gaussian processes are not as famous as they could be. So the inversion of a matrix of n cross n is order n cubed, right, which is a very expensive computation. Imagine if you have a lot of train points. So the really interesting thing about Gaussian processes is, let's say that, let me take you back to this thing, right? So what I'm showing here is that, let's say we have train points, n star test points. If n and n star are increasing, then this covariance matrices that you need to draw are also becoming very large. So this algorithm does not scale very well in terms of the number of train points or test points, which is a huge concern. Nevertheless, there are some techniques called sparse Gaussian processes which try to solve this problem. So which try to pick up a set of representative points instead of all possible train points that we have. But the problem that I'm going to now discuss is not about reducing the complexity of Gaussian process update calculation, but about making it numerically more stable. So often if the matrices are poorly conditioned, then the calculations are numerically very unstable. And this is where Cholesky or Cholesky decomposition is very often used in the literature. So many times, even when you do anything like linear regression, etc., you would end up using Cholesky decomposition instead of just finding the inverses, right? So what I'm going to say is that I'll be writing that the the probability of y star given x star the test input and the train input x and the train output y is a normal with a mean mu tilde sigma tilde. I'm going to write k. K was the uh, kernel is the kernel matrix where it's a covariance matrix which is found out by applying the kernel function over the train input with the train input. So I'm going to write it as LL transpose. So this is done via the Cholesky decomposition. So I'll be also introducing some amount of notation here. So I'll be saying that if A omega equal to B, then omega is A, the symbol which is similar to divide symbol, B, right? So I'm now what I'm trying to do is to write this entire computation. This computation where there were a lot of inverses, and in terms of LLM transpose. Right? So what I'm going to say is that alpha is k inverse x minus mu. So if we go back, we had written, so mu tilde is mu star plus k star transpose k inverse x minus mu, right? So this inverse is what we're trying to get rid of. And we think that we'll be using Cholesky decomposition over here. I've defined k to be LL transpose. I've defined alpha as k inverse x minus mu. I'll replace k with LL transpose, and this entire thing is inversed, and then I'm multiplying with x minus mu. So I can rewrite alpha to be L transpose inverse time L inverse multiplied by x minus mu. I'm going to be now looking at this thing, which is L inverse x minus mu. I'm going to call it to be gamma, right? So we have L inverse x minus mu equal to gamma. I pre-multiply both sides by L. I can get L gamma equal to x minus mu, which is of this form. A omega equal to B, then omega is A by B. Thus I can write gamma to be L, I'll just call the symbol for now, divided by L divided by x minus mu, which is effectively trying to solve this linear system. So, and similarly I can write alpha is the solution to this equation, L transpose L and x minus mu, right? So the good thing about Python is that it's fairly simple to write this in Python. All I need to do is to first compute L as a Cholesky decomposition of K, and then I can write alpha equal to numpy dot linear algebra dot solve L dot transpose, and the other side is L and x minus mu. So this is again a numpy dot linear algebra dot solve of L and x minus mu, right? So having now written alpha in this particular fashion, we can then just write mu tilde as mu star plus k star transpose alpha, right? And we can also, let's try to see what we can do about this sigma tilde term. So the sigma tilde term was k star star minus k star transpose k inverse times k star, and what we'll want to do is to write this term also more efficiently in terms of the Cholesky decomposition. So I'll be firstly writing V as solving this linear equation L and K star. So basically that means that V equal to L inverse K star. I can write then V transpose as a transpose of this entire thing. So that will be K star transpose and L inverse transpose. I can write V transpose V as the product of these things. So effectively what I wanted to do was to get a K inverse term, right? So I want to get an L inverse and L term. So I'll basically write as K V transpose V as K star transpose, N inverse transpose multiplied by L inverse, and finally K transpose. And thus we can write this as K transpose, K star transpose. This entire thing we can write as K inverse. So if we see what we've written as K inverse. So K inverse is LL transpose the whole inverse, which is L inverse transpose times L inverse. So that's L inverse transpose times L inverse is just K inverse times K star, right? So K star transpose K inverse, K star can be written as K star star minus sigma tilde. This is given by this formula. So sigma tilde is K star star minus K star transpose K inverse times K star. Thus, we can do a much more efficient, better conditioned computation of sigma tilde is equal to K star star minus V transpose V. So what I've now done is to rewrite the above function for the case of noiseless GP with the Cholesky decomposition. So everything else remains the same. Just that I'll first define this L term, which is Cholesky decomposition. I'll be rewriting the means and the posterior mean and the posterior covariance in terms of the L's and the V's. So if you notice, first I'm defining L, which is a Cholesky decomposition on K. So K is, remember, the kernel computation between the train and the train. And I've defined now alpha, which is numpy.linearalgebra.solve as I'd shown earlier. I've defined a V, and I've finally written the posterior mu and the posterior sigma in terms of L and V's. I've learned the prediction. I've fitted now the noises GP with Cholesky decomposition on the same train data, and I've just done the comparison that the posterior means that I'm getting over the Cholesky decomposition versus I'm getting without the Cholesky decomposition using the inverse are exactly the same, and that's the same I'm getting even in terms of the posterior variances. So far so good. Now let's look at the final thing to make our discussion more concrete. So thus far we've been assuming a noiseless model. So by a noiseless model I mean that whenever there is any conditioning, so whenever we have observed any points, then there is no variance about it. There is nothing unknown about that. But we'll now be making a noisy GP assumption, which is to say that instead of writing yi equal to f of xi, we can write yi equal to f of xi plus epsilon. That about each point there is some observational noise epsilon, which is normally distributed with a mean 0 and a variance sigma y star. So the only thing which we now need to change is just the definition of the kernel or the covariance matrix K, which is between the train points and the train points. We're going to replace that with a K sub y, which is just adding the variance term multiplied by the identity matrix of size n by n, given that n is the size of the train points, plus the previous defined K matrix coming from the covariance function, kernel function. So I've just done that changes. If we see that I've defined self.k here, and so the only change is now that I've added self.sigma y multiplied by an identity matrix of the length of identity matrix of size of length of train x by train x, and everything else remains the same. I have fitted it on a dataset, the same dataset, and now you can see that even at the training points, there is some amount of variance. There is not zero variance over there. Right? So there is some amount of uncertainty over there. So I'll just try to recap the entire discussion. We had started off with understanding about how 1D Gaussians look like, how we can sample from them, and then we started with the bivariate Gaussian. We looked at the marginalization and conditioning of bivariate Gaussians, and we said that they are still, again, 1D Gaussians. We had then looked at the case where we were plotting, we were drawing samples from a 2D Gaussian, where we showed a covariance matrix, a contour plot, and a visualization, different kind of a visualization. And we saw that we can just uh, plot these two random variables in this case based on the sample point. We showed an animation which was showing the different samples which could have been drawn. Since the covariance is not very high, the correlation between x1 and x2 is not very high, we see that the samples drawn also don't reflect x1 and x2 be similar. But in another case, we saw that the covariance matrix was structured like this. The correlation was significantly high. The contour was much more elliptical in nature and much more closer to being a line. We saw that x1 and x2 are going to move very close to each other always. We then discussed about conditioning in the bivariate Gaussian case. So we fixed in this example x1 to be a certain value 1 in this case. Since the covariance matrix is structured like this, the correlation is high. X2 would be fairly close to x1 in its mean, and the variance would also be low. We repeated the same procedure for high dimensional Gaussians, in this case a 5D Gaussian. We did some observations. We then said that if we observe some points, or we can condition on some points, then we can get a conditional distribution, which is again a high dimensional multivariate Gaussian distribution. We repeated the same procedure now for case of 20 dimensions, but we saw that we would have had to use the kernel function because specifying a covariance matrix of 20 cross 20 is non-trivial. What we see in this diagram is the interpretation is going to help us interpret the Bayesian setting of Gaussian processes. What we see is now the prior over all the possible functions which could have been drawn based on this multivariate Gaussian. Once we observe some points, so we do some conditioning or we observe some points, then the family of functions will change. So that's exactly the Bayesian setting. We have a prior over the functions and you have a posterior over functions, which depends on the data and the prior of the functions. We looked at a formal definition of Gaussian processes after having gone through some understanding of the kernel function. And we can formally define a GP based on a mean function. Typically that is set to 0, assuming that you'll center the data, and a covariance matrix, which is a covariance function which defines the relationship between 2 points. And we've seen that there is a beautiful conditioning formula which gives us the posterior mean and the posterior covariance matrix. We said that we could solve this. We wrote a scikit-learn like function where we were trying to solve this for using the inversion formulas. So because of inversion, GPs are computationally very hard and they scale cubic in the number of points, which is not very good. Some sparse methods have been proposed also. We said that this is all good, but this is not very well conditioned for inverting such matrices. That is where Cholesky decomposition comes into place. We saw how we can derive the formula for Cholesky decomposition for the case of Gaussian process regression. And finally, we discussed the case for noisy GPs, which assume that even at the points which you have observed, the train points, you can have some amount of noise. With this, I'll end today's lecture. I hope it's been of use to you. It's somewhat difficult thing to understand at first, but if you go through it slowly and go through the notebook, running the notebook on your own, you'll get a much better understanding of how Gaussian processes work. Hopefully in a future lecture, I'll talk about some examples to make Gaussian processes understanding even better.